Avi Loeb raised concerns early on that 3I Atlas didn't fit the template of a natural comet, and the new HiRISE images are revealing the anomalies he was talking about. 3I Atlas is confirmed to be interstellar, its trajectory unbound, and its composition atypical compared to long-period comets. It brightened irregularly as it approached the Sun, and its carbon dioxide-rich coma does not match the behavior expected from a small, intact, icy nucleus. Now, NASA's HiRISE camera has captured the highest resolution images of 3I Atlas so far. These observations show a compact nucleus wrapped in an asymmetric halo and jet structures that do not follow the patterns predicted by standard comet physics. Some of these features are confirmed, some remain unverified. Several are still under active scientific review. In this video, we'll break down what the images actually show, what researchers agree on, and which anomalies remain unresolved. If you're finding value in this deep dive, gently tap that like button and subscribe. Tell me in the comments where you're listening from, what time it is there, and what you think is the most compelling anomaly about 3I Atlas. NASA released only a brief technical summary ahead of the HiRISE data, but even that limited description was enough to raise eyebrows. The images show 3I Atlas as a single, bright nucleus, roughly consistent with early diameter estimates, but the surrounding coma is uneven, extending farther in one direction than the others. This asymmetry isn't unusual by itself, but what stands out is the way the brightness gradients change across the halo. Instead of a smooth fade, the HiRISE data shows pockets of enhanced reflection, as if certain regions are ejecting material more aggressively than others. In standard comet physics, strong asymmetry usually points to seasonal heating or localized jets triggered by sunlight, striking volatile-rich areas. Researchers examining early 3I Atlas data noted this possibility. But when they compared the HiRISE structures with previous infrared measurements from Webb, something didn't align. The regions that should have been most active thermally were not the ones producing the brightest reflections. So far, this is not a confirmed contradiction, just an observation that the energy distribution across the surface isn't following the expected pattern. Another detail in the HiRISE release was the orientation of the faint jets extending from the nucleus. These jets appear slightly off-axis, not aligned with the direction of solar heating. In most natural comets, jets roughly align with the sunward face of the nucleus, where sublimation is strongest. But in the 3I Atlas images, at least one jet appears angled away from that expected geometry. This feature is still being evaluated, and astronomers caution that image resolution limitations could make the orientation appear more pronounced than it is. Still, it's an anomaly worth noting. The HiRISE data also offers a clearer look at the comet's surface texture. Although the nucleus cannot be resolved with perfect clarity, the brightness patterns suggest a rough, irregular body, rather than a smooth spherical shape. This is typical for comets, but the contrast difference between the brightest and darkest regions is unusually sharp. Early commentary from mission scientists described the object as highly structured, a phrase that has raised questions, but currently has no confirmed technical meaning beyond describing brightness variation. It's important to emphasize that none of these observations imply anything unnatural. Every detail so far has at least one plausible cometary explanation. However, the pattern of irregularities, asymmetric jets, uneven mass loss behavior, and inconsistent surface heating signatures collectively hints that this object is not behaving like a standard carbon dioxide-dominated comet. Where things become more interesting is in the timing of the activity. HiRISE captured 3I Atlas during a phase when its overall brightness should have been stabilizing. Instead, the data suggests a brief period of increased output on one side of the nucleus. Whether this represents fragment shedding, volatile release, or simply surface rotation is still unknown. No confirmed fragmentation is visible in the HiRISE images, but the asymmetric coma could indicate recent activity. And this leads to a larger question. Why does 3I Atlas show multiple independent signs of uneven acceleration and mass shedding while remaining a single, compact source in the HiRISE images? That contradiction is at the center of the next set of observations. Before the HiRISE images were captured, multiple observatories had already been tracking 3I Atlas. These earlier datasets form the baseline that scientists now compare against the new, higher resolution views. One of the first surprises came from the James Webb Space Telescope. Webb's infrared spectrographs detected an unusually large carbon dioxide cloud surrounding the nucleus, far larger than expected for an object estimated to be roughly 1 to 2 kilometers across. CO2-rich Comet are not unheard of, but the scale here exceeded typical sublimation models for a small interstellar body. Webb also recorded small but persistent variations in brightness across different wavelengths. These changes were real, but their interpretation remains uncertain. They could represent rotation, uneven ice distribution, or localized jets. None of these explanations are confirmed yet. What puzzled astronomers was that the timing of the brightening didn't match a simple rotational pattern. The intervals were irregular, suggesting either an uneven surface composition or a more complex nucleus shape than early models predicted. Hubble provided another layer of information. High-contrast images taken weeks apart showed subtle changes in the shape of the coma. The outer halo expanded unevenly, with one side consistently appearing brighter and more diffuse. This asymmetry is consistent with jet activity, but the direction shifted slightly over time. In a typical comet, jet alignment remains relatively stable unless the nucleus undergoes a major thermal or structural event. No confirmed fragmentation was detected in the Hubble data, yet the shifting asymmetry hinted at changes occurring beneath the surface. Ground-based observatories added their own details. Several teams reported that 3I Atlas's non-gravitational acceleration, the slight push, not explained by gravity alone, fluctuated more than expected. These fluctuations were not extreme, but they were noticeable. Variations like this are normal in active comets, but for an interstellar visitor with unusual chemistry, scientists paid closer attention. So far, these acceleration measurements are still being refined, and researchers caution that uncertainties remain high. When these early observations are placed side by side, a pattern emerges. Webb showed an oversized CO2 cloud. Hubble documented a shifting asymmetric halo. Ground-based telescopes measured variable non-gravitational acceleration. Each dataset alone can be explained with standard cometary activity. But together, they suggest that 3I Atlas may have an unusually complex structure or an irregular rotational state. This aligns with the HiRISE findings of uneven jets and brightness pockets around the nucleus. The challenge is that none of the earlier telescopes could resolve the nucleus itself. They saw the halo, the jets, the coma structure, and brightness changes, but never the solid core. HiRISE is the first instrument to produce images sharp enough to hint at surface-level behavior, and it adds an important constraint. Despite irregular activity, the object appears intact. This intact appearance conflicts with a speculative interpretation proposed by some researchers, including Avi Loeb, who suggested the comet might have undergone partial fragmentation or rapid structural change. That idea is not supported by the HiRISE data so far. The nucleus appears compact, without obvious signs of breakup. However, the mismatched activity patterns remain unexplained. Why do multiple telescopes detect inconsistent heating signatures? Why does the brightness modulate irregularly? Why does the non-gravitational acceleration fluctuate without a clear rotational period? HiRISE answers one set of questions but opens another. What internal structure could produce these surface-level anomalies while remaining a single, intact body? To make sense of these mixed signals, most scientists start with the simplest framework: 3I, Atlas as a very active, irregular comet whose surface and spin just happen to be complex. The first mainstream explanation focuses on shape and rotation. If the nucleus is elongated, lumpy, or fractured internally, different regions could turn in and out of sunlight in a way that doesn't produce a neat, repeating brightness pattern. Combined with a tilted spin axis, this could explain why the jets and heating signatures appear inconsistent across Webb, Hubble, and HiRISE. This scenario is consistent with what we know about many solar system comets and is currently considered the most conservative interpretation. It's plausible, but not yet fully confirmed, because the nucleus is still too small to map in detail. A second explanation involves layered volatiles. In this model, 3I, Atlas carries bands or pockets of different ices: carbon dioxide, carbon monoxide, water, and organics stacked beneath its surface. As the object heats unevenly, specific patches suddenly turn on, driving localized jets without a simple rotational rhythm. This could account for the oversized CO, coma, and irregular brightening. The idea of layered volatiles is well supported in comet science generally, but for 3I Atlas, it remains an inference based on indirect data, not a direct measurement. A third line of thinking considers thermal stress and microfracturing. Even if HiRISE sees a single compact body, the outer layers could be cracking and venting in small regions, redistributing material without fully breaking the nucleus apart. This might explain short-lived surges in one-sided activity and subtle shifts in the non-gravitational acceleration. Again, this is consistent with known comet behavior, but no direct fractures have been resolved at 3I Atlas's distance. It is still a working hypothesis. Beyond these relatively standard models, there are more speculative ideas. Some researchers have suggested unusual material properties, such as a higher than expected metal content or exotic ice phases that could alter how the surface responds to heating. These concepts are, at the moment, theoretical and not backed by peer-reviewed confirmation for this specific object. They are useful as thought experiments, but remain unproven. Finally, there is the most speculative category, the notion that 3I Atlas might be partly artificial or technologically modified. This idea sometimes appears in public discussions and opinion pieces, occasionally referencing the object's interstellar origin and anomalous activity. However, there is currently no verified evidence supporting a technological interpretation. All peer-reviewed analyses so far treat 3I Atlas as a natural body with unusual but potentially explainable characteristics. Any technological or engineered explanation remains firmly in the realm of speculation. What all of these models have in common is that they are trying to reconcile the same core tension: a small, intact nucleus producing outsized, uneven activity that doesn't map cleanly onto simple rotation or uniform heating. And this is where the HiRISE images become especially important, because they don't just show an odd comet, they also define what cannot be happening on its surface. Next, we'll look at what the HiRISE data silently rules out and what kinds of behavior 3I Atlas is almost certainly not exhibiting. The HiRISE images don't only highlight anomalies, they also provide constraints. They show what 3I Atlas is not doing. This is important because ruling out behaviors narrows the field of viable explanations and helps separate realistic models from ones that conflict with direct observation. The first clear constraint is no visible large-scale fragmentation. Earlier speculation suggested the comet might have split into multiple major pieces before or near perihelion. HiRISE does not support that. The images show one compact brightness source with no resolved secondary nuclei. While microfragmentation below resolution is possible, large or mid-sized fragments are not present in the available imagery. This eliminates any scenario requiring dozens of separated bodies or major breakup events. A second constraint comes from jet geometry. The jets captured by HiRISE appear localized but relatively short, and their brightness diminishes quickly with distance. This rules out extremely high-speed outflows or coordinated jet networks, sometimes proposed in more speculative discussions. The object is active, but the jets behave within the general range of natural comet outgassing, albeit in directions that aren't fully expected. Their scale is simply not large enough to imply controlled propulsion or synchronized emission patterns. Their angles may be unusual, but their energy is not extraordinary. A third limit is surface smoothness. While the nucleus is unresolved at fine scales, brightness gradients show no indication of the smooth, planar surfaces that would be expected from artificial shaping or engineered panels. The reflectivity pattern is patchy and irregular. This strongly favors a rugged, natural surface. No consistent edges, repeating patterns, or geometric textures appear in the modeled brightness profiles. Another important negative result: no extreme outbursts. Although earlier observations showed irregular brightening, HiRISE does not indicate any violent ongoing event, such as a sudden mass loss spike. The coma appears stable at the time of imaging. This suggests that whatever caused earlier fluctuations had either subsided or was localized enough not to alter the broader structure. The object is active, but not erupting dramatically at the moment of observation. HiRISE also helps rule out binary rotation models. The nucleus's light distribution does not show the characteristic dual-lobed patterns that appear in some comets formed from fused pairs. While it could still be irregularly shaped, the brightness center is consistent with a single dominant mass, not two bodies locked in contact rotation. These constraints simplify the problem. They eliminate large-scale fragmentation, extreme jets, engineered surfaces, violent outbursts, or dual body structures. What remains is a small, rugged, intact, interstellar nucleus, producing uneven activity through mechanisms that are natural but not yet fully understood. This places 3I, Atlas, in an unusual category. An object that exhibits only subtle anomalies, but does so consistently across multiple instruments. No single feature is extraordinary on its own. The puzzle comes from the combination asymmetric jets, irregular heating signatures, fluctuating acceleration, and oversized CO2 release, all happening together, while the nucleus remains intact. And this brings us to the next question. What about the interstellar origin of 3I? Atlas might make it different from comets native to our solar system. To understand why 3I Atlas behaves differently from most comets observed in our solar system, scientists look to its origin. Interstellar objects are shaped by environments that can differ significantly from the conditions in our own protoplanetary disk. Temperature, stellar radiation, chemical abundance, and formation history can all be different. These differences matter because they determine what an object is made of and how it reacts when it enters a new solar system. One possibility is unusual ice chemistry. In colder or more metal-rich regions of the galaxy, ices like carbon monoxide and carbon dioxide can accumulate in larger quantities relative to water. If 3I, Atlas formed in a region with abundant CO2, SPO, rich ice, that would explain the oversized carbon dioxide coma detected by Webb. This idea is scientifically plausible. It fits with known variations observed in exoplanet-forming systems and is consistent with the composition of some interstellar dust samples. Still, this remains an inference for 3I, Atlas specifically, not yet confirmed through direct measurements. Another factor is surface layering, caused by interstellar travel. As the object moved between stars over millions of years, cosmic radiation could harden its outer layers, creating a crust that traps volatile ices below. When it finally entered our solar system and warmed, these trapped deposits may have begun to vent through narrow openings. This could produce the uneven jets and irregular brightening observed across multiple telescopes. Radiation-induced crusting is well documented in small bodies within our own system. So extending this idea to an interstellar traveler is reasonable, though still theoretical, until sampling is possible. A third explanation involves thermal fatigue from repeated temperature swings. Interstellar space exposes objects to wide thermal extremes, deep cold far from stars, then sudden heating during close stellar passes. Over time, this can produce internal cracks, voids, and density variations. These internal structures might cause sublimation to occur in unpredictable patterns, matching the irregular activity seen in 3I, Atlas. This mechanism is grounded in known physics, but remains unverified for this object. Some astronomers also consider the possibility of non-uniform material distribution. If 3I, Atlas formed in a chaotic environment, perhaps near a young star or within a dense molecular cloud, its building blocks may not have been evenly mixed. Pockets of different materials could produce localized activity, irregular heating signatures, and fluctuations in acceleration. This model is scientifically reasonable. Many solar system comets also show compositional variations, though the degree required to explain 3I, Atlas's behavior is still under debate. Taken together, these interstellar formation scenarios paint a picture of a body that is natural but fundamentally different from the comets we typically observe. That difference does not imply anything artificial. It simply reflects origins in an environment we have little direct experience with. If 3I, Atlas carries chemistry or internal structures common in other star systems, then its activity patterns may simply represent physics operating under unfamiliar conditions. The challenge is that none of these ideas can be confirmed with the available data. They remain scientifically grounded hypotheses that fit parts of the puzzle, but not every detail. The object's intact nucleus, oversized CO2 coma, irregular jets, shifting asymmetry, and fluctuating acceleration still lack a single, clean explanation. Each model answers one part of the story, but not the whole. And this leads to the next critical question. What do the upcoming telescope campaigns, Webb, Hubble, and ground-based arrays aim to measure? And why are these next observations so important? The next phase of observation is crucial because the existing data leaves too many open questions. NASA, ESA, and several ground-based observatories have already scheduled targeted campaigns designed to capture the comet at key moments in its trajectory. Each instrument contributes a different piece of the puzzle. Together, they may determine whether 3I Atlas fits comfortably within natural comet physics or requires new models to explain its behavior. The first set of measurements will come from Hubble's ultraviolet spectrographs. Ultraviolet data helps identify specific volatile compounds and track how they evolve as the object continues to heat and rotate. Scientists want to know whether the CO2-rich coma detected by Webb remains dominant or if new compounds begin to appear. Consistent composition over time would strengthen the idea that 3I Atlas simply contains an unusually large reservoir of certain ices. But if the spectral signatures shift irregularly, it would suggest a more complex internal structure. These results are pending and not yet public. A second objective lies with James Webb's mid-infrared instrumentation, which will observe the nucleus and coma during different phases of solar heating. Webb's infrared sensitivity can detect subtle changes in temperature and dust emission. Researchers hope to confirm whether the earlier brightness fluctuations were caused by rotation, localized jets, or thermal stress. If Webb finds stable thermal patterns, that would support the rotation-based explanation. If the patterns remain inconsistent, scientists will need to refine or replace current models. As of now, these observations are scheduled but not yet released. Ground-based telescopes will play a key role as well. Several major observatories are preparing to measure precise non-gravitational acceleration over the coming weeks. These measurements help determine exactly how jets influence the comet's motion. If the acceleration stabilizes, it would indicate the object is settling into a more predictable outgassing pattern. If it continues to fluctuate, it would reinforce the idea that the activity is driven by uneven subsurface structures. The data is still being collected, and early estimates carry large uncertainties. Another area of focus is coma morphology, the shape, asymmetry, and rotation of the halo surrounding the nucleus. Hubble, Webb, and ground-based optical arrays will compare the coma over time to see if the direction of jet activity remains consistent or shifts unpredictably. A stable jet orientation would support simple thermal models. Shifting orientation without a clear rotational period would suggest more complex internal dynamics. This analysis is ongoing. Researchers also want to determine whether the object experiences microfragmentation on scales too small for HiRISE to resolve, but large enough to affect the coma. This can be detected through changes in dust, grain, size distribution measured through infrared and ultraviolet spectroscopy. If microfragmentation is occurring, it could explain the irregular coma structure without requiring major fragmentation events. These measurements are planned, but not yet complete. All of these investigations share a common goal: to determine whether 3I Atlas fits into an extended range of natural comet behavior, or whether it represents something that requires new physical models. At this point, no result rules out natural explanations, but none of the existing data points confidently toward a single one. The upcoming observations are structured to reduce this ambiguity. The next few weeks will therefore be a turning point. If the new data confirms stable rotation, predictable spectral changes, and consistent jet geometry, the story will become clearer. If the inconsistencies persist, the scientific discussion will shift toward more complex interpretations. And that leads to the next layer of analysis: what outcomes astronomers expect, and what each outcome would mean for our understanding of interstellar objects. As new data approaches, astronomers are preparing for several possible outcomes. Each scenario would tell a different story about what 3I Atlas is, how it formed, and why it behaves in ways that don't neatly match existing comet models. None of these outcomes require anything beyond known physics, but each carries implications for how we interpret interstellar visitors in the future. The first scenario is the stabilization model. In this outcome, new observations show a consistent rotational pattern, predictable heating signatures, and jets aligned with the sunlit surface. If this occurs, it would suggest that earlier anomalies were simply the result of temporary outgassing states as the object adjusted to solar heating. Many comets behave erratically early in their approach, then settle into a more regular pattern. This would place 3I Atlas at the far end of normal comet behavior, but still within the bounds of natural variation. This scenario is considered plausible, though not yet supported by any confirmed rotational signal. A second scenario is the complex natural activity model. Here, the new data would continue to show irregular jets, fluctuating brightness, and changing asymmetry in the coma. This outcome would suggest the object has an unusually chaotic internal structure, layers of different ices, fractured pockets, or density variations built up over millions of years of interstellar exposure. This would not indicate anything unnatural, but it would push scientists to expand models of how small bodies behave after long periods in deep space. This scenario aligns with many of the unresolved patterns seen so far. A third possibility is the intermixed chemistry model. If new spectroscopy shows shifting ratios of CO, 2CO, water ice, and organics, it would indicate that 3I Atlas contains complex internal layering or source regions that activate at different temperatures. Comets in our solar system show some of this behavior, but the scale required to match early observations would be larger than usual. This scenario is scientifically plausible, but remains unconfirmed without additional spectral data. The fourth scenario is the external fragmentation model, where new observations detect small, previously unseen fragments trailing the nucleus. HiRISE did not show major fragmentation, but microfragments below its resolution could still exist. If detected, this would connect the oversized CO2 cloud and shifting activity to a gradual structural breakdown. This scenario is speculative, but physically possible. No fragments have been confirmed so far. The most speculative outcome is the structural anomaly model, where new data reveals organized jet patterns or acceleration signatures not well explained by standard comet physics. This does not imply artificial behavior. It may simply indicate we lack the right physical models for certain interstellar compositions. This scenario is the least defined and would require clear, repeated evidence. At the moment, there is no verified observation pointing in this direction, but it remains one of the possibilities scientists must consider if data continues to defy current expectations. What all these scenarios highlight is the same underlying idea. 3I Atlas is at a point where new data could meaningfully change the interpretation of what we're seeing. The next set of measurements won't just refine existing models, they could determine which models are even viable. If the data turns out clean and consistent, the story becomes one of unfamiliar chemistry and internal structure. If the data remains erratic, the scientific focus shifts to how interstellar conditions produce small bodies with unpredictable activity. And if the data exposes patterns inconsistent with current models, new theoretical work will be required. Each outcome is scientifically valuable, but they paint very different pictures of the object. And that leads to the final question: what exactly will NASA's HiRISE images, combined with upcoming telescope campaigns, allow us to conclude about 3I Atlas, and what uncertainties will remain even after all the data is collected? Bringing all the data together, from HiRISE, Webb, Hubble, and ground-based arrays, scientists are starting to converge on a general picture of what 3I Atlas likely represents. This picture is still incomplete, but certain trends are becoming clearer as more observations accumulate. The most consistent interpretation so far is that 3I Atlas is a small, intact interstellar comet with an unusually complex internal structure and an atypically high concentration of carbon dioxide rich volatile material. This explanation aligns with the oversized CO2 coma, the irregular jets, and the fluctuating non-gravitational acceleration. It also fits with what HiRISE shows: a compact nucleus with no large fragments, surrounded by asymmetric but not extreme activity. This model suggests the comet likely formed in a region of its native star system, where carbon dioxide and other volatiles were more abundant relative to water. Such variations are common in protoplanetary disks. If 3I Atlas was ejected early in its system's history, it may have preserved these primordial layers through millions of years of interstellar travel. This scenario remains scientifically reasonable and carries no speculative assumptions beyond known comet physics. Another likely component is internal heterogeneity, uneven pockets of ice's materials distributed through the nucleus. This would produce localized jet activation, irregular heating signatures, and brightness fluctuations that do not follow simple rotational patterns. It matches the deviations seen across Webb and Hubble, and explains why the HiRISE images show multiple small jets oriented in non-standard directions. This interpretation is not yet confirmed, but is supported by several indirect lines of evidence. The remaining question is why the activity patterns are so inconsistent. This is the point where multiple models remain viable. Thermal fatigue, interstellar radiation crusting, internal cracks, and volatile layering all remain possible contributors. None have been ruled out. It is likely that the comet's behavior is the result of several of these processes acting at once, rather than a single dominant mechanism. What does seem increasingly unlikely based on the current data is any scenario requiring major fragmentation, artificial structure, or non-physical behavior. HiRISE has narrowed these possibilities by showing a stable nucleus, natural jet intensities, and irregular but not excessive asymmetry. As more measurements arrive, these speculative interpretations will likely continue to lose support unless new evidence emerges. However, not everything will be resolved. Even with the full set of observations, scientists expect that some uncertainties will remain permanent. Interstellar objects are rare, and each one offers only a brief window of opportunity. 3I Atlas will continue moving away from the inner solar system, and by early 2026, many of its features will become too faint to measure with precision. Its rotation state, detailed composition, and internal structure may never be fully mapped. But what the data will likely give us is a coherent explanation grounded in physics: an interstellar comet with an unusual composition, a rugged, intact nucleus, complex but natural sublimation patterns, activity shaped by conditions unlike those in our own solar system. This conclusion does not diminish the object's scientific value. It highlights how much variation exists among bodies formed under different stellar environments. The story of 3I Atlas is ultimately about encountering something shaped by a world we have never seen, a fragment of a distant system passing through ours, carrying traces of its origin. And that leads us to the final, broader question. What does studying 3I Atlas teach us about interstellar objects as a whole? And how will it shape the way we interpret the next visitor that enters our solar system? Even as scientists begin assembling a clearer model of 3I Atlas, one issue continues to stand out: the scale and behavior of its mass loss. Across multiple telescopes, including Webb and several high-sensitivity ground-based instruments, the total rate of material flowing off the comet has been consistently higher than expected for an object of its size. This pattern is not extreme, but it does sit at the upper limits of known comet activity. Understanding this discrepancy is a priority because it informs nearly every other aspect of the comet's behavior. Researchers currently consider three main explanations for the elevated mass loss. The first involves enhanced volatile content. If 3I Atlas contains unusually large stores of carbon dioxide and carbon monoxide, far more than a typical water-dominated comet, then its activity would naturally be stronger. These ices sublimate at lower temperatures, so even mild sunlight could trigger rapid outflow. This explanation matches early spectral data, but is not fully verified due to the lack of long-term compositional measurements. A second explanation is unusual thermal conductivity. If the comet's surface transfers heat more efficiently than expected, larger areas of the nucleus would warm at once, generating widespread sublimation. This could produce the oversized coma and rapid mass loss without the need for an exotic composition. Such an effect could arise from dense, carbon-rich material or fine-grained dust layers accumulated during interstellar travel. This remains a theoretical model, but fits the general physics. A third possibility involves hidden internal reservoirs. In this scenario, the comet contains structurally isolated pockets of volatile ices that are beginning to vent through narrow fractures. As these pockets activate at different times, the mass loss appears irregular and elevated. This idea aligns well with the shifting jets and asymmetric coma structure. It also predicts that new vents may appear as the nucleus continues to warm, which future observations can test. Another active research area involves the comet's rotation state. If 3I Atlas is rotating irregularly or even tumbling, it would expose different surface regions to solar heating in unpredictable ways. This would naturally explain the inconsistent jet orientation and the lack of a clean periodic brightness pattern. However, confirming a tumbling state requires precise light curve measurements, and so far, no definitive rotational period has been detected. Scientists are still collecting data, but the window to identify a clear signal is narrowing as the comet's brightness declines. The structure of the coma itself raises additional questions. Several observatories have reported faint, transient features within the halo, subtle arcs, uneven diffusion regions, and temporary enhancements that appear and fade over timescales of hours or days. These features are not uncommon in active comets, but the frequency of their appearance in 3I Atlas is higher than average. The cause remains uncertain. Some researchers suggest that shifting vents give rise to these localized patterns. Others propose that dust grain properties, size, composition, or charge may influence the way material disperses. Taken together, these behaviors point toward a nucleus that is more dynamic and internally complex than typical comets. Nothing in the data requires exotic explanations, but the coordinated presence of multiple unusual features continues to challenge standard models. This is why researchers are pushing for as many observations as possible while the comet remains accessible. Each new dataset targets a different piece of the puzzle. As the comet moves through its current phase, scientists are watching closely for any signs of activity, transitions, subtle shifts in the rate of sublimation, changes in jet geometry, or modifications in the coma's size and structure. If these transitions occur, they may help identify which models best fit the comet's behavior. One key question now emerging is whether 3I Atlas is approaching a stage where its activity will begin decreasing, or whether it still has periods of stronger outgassing ahead. As 3I Atlas continues moving away from the Sun, one of the most important scientific questions is how its activity will change. A comet's behavior normally follows a predictable trend. Activity increases as it approaches perihelion, peaks near maximum heating, and then steadily declines. But because 3I Atlas is interstellar, scientists cannot assume it will follow this pattern. Its chemistry, internal structure, and thermal response may behave differently as conditions shift. Most models predict that 3I Atlas should begin gradual stabilization. As the nucleus cools, volatile ices near the surface may become dormant, reducing jet activity. This would lead to a smoother, more symmetric coma and fewer abrupt brightness fluctuations. If this happens, it would support the interpretation that the earlier anomalies were simply the comet cycling through its most active phase. Scientists expect some degree of decline, but the timing and speed remain uncertain due to the comet's unusual composition. Another possibility is delayed activation of deeper volatile pockets. If the nucleus has layers of buried CO, 2CO, or other volatiles beneath a hardened crust, then heat absorbed near perihelion may continue propagating inward even after the comet moves away from the Sunday. This can trigger new jets or cause existing ones to intensify. Several solar system comets show this type of delayed activity, though not all. If 3I Atlas activates deeper layers in this way, the result may be new asymmetry in the coma or shifting jets that do not follow a straightforward decline. This behavior is plausible, but remains unverified until more data arrives. A third, expected trend is continued irregular acceleration. Even as activity declines, small jets can still alter the comet's trajectory. Researchers are watching for subtle changes in the non-gravitational acceleration, whether it stabilizes, fluctuates, or reveals new directional patterns. A stable decline would support thermal models. Persistent fluctuations would imply a more chaotic internal structure. Sharp directional shifts would require careful analysis to determine whether they come from sublimation or measurement noise. So far, no clear trend has emerged. Another area scientists are monitoring is the coma's morphology. As the comet cools, the halo should contract and become more uniform. But if structural vents beneath the surface remain active, the coma could continue displaying uneven arcs, streaks, or faint shell-like patterns. These features, while natural, would indicate ongoing internal changes even as the nucleus cools. Ground-based observatories will track these transitions closely because changes in coma shape can reveal whether new jets are forming or old ones are fading. Spectroscopy will also play a major role in determining how the comet evolves. If the ratio of carbon dioxide to water ice changes significantly, it would suggest that different volatile layers are being exposed over time. If the ratio remains consistent, it implies a more uniform subsurface composition. Both outcomes are scientifically informative. Scientists expect some degree of spectral change as the comet cools, but the scale of that change will help determine which formation and structure models best reflect reality. A final factor is the possibility of surface restructuring. Even if the nucleus remains intact, thermal cycles can shift dust layers, collapse small cavities, or expose new patches of ice. These microscale changes are not detectable directly at 3I, Atlas's distance, but they manifest through changes in brightness patterns and coma behavior. Observers will compare upcoming images to earlier data to look for signs of such subtle evolution. All of these expected changes, stabilization, delayed activation, shifting spectral ratios, and structural adjustments, depend on the interaction between the comet's composition and the sun's fading heat. This is why continuous observation matters. Interstellar objects behave differently from anything formed in our solar system, and each measurement gives insight into conditions around another star. The question now is what kind of long-term behavior 3I Atlas will settle into as it continues outbound. Will it become a quiet, cooling object that fades predictably? Or will it continue showing irregular patterns that challenge simple models? As 3I Atlas moves deeper into its outbound leg, its trajectory becomes an equally valuable source of information. The path an active comet follows is shaped not just by gravity, but by the subtle forces produced by jets on its surface. These non-gravitational accelerations are usually small, predictable, and mathematically well understood. But for 3I Atlas, the measurements taken so far have not cleanly matched the simplest models. The inconsistencies are minor, yet persistent, and that persistence suggests that analyzing the outbound trajectory may reveal more about the comet's internal layout than we currently understand. One of the key questions is whether the jet-induced forces will begin to stabilize. In a typical comet, once peak activity passes, the dominant jets remain active in predictable ways as the surface cools. If the acceleration of 3I Atlas becomes steadier in the coming weeks, it will indicate that the object's most volatile layers have already been depleted and that deeper layers are responding more uniformly. This outcome would support the model of a layered nucleus with initially uneven activation. A second possibility is that the acceleration will remain irregular, with subtle directional changes that do not follow a simple cooling curve. If this occurs, scientists will consider the likelihood of multiple internal reservoirs activating at different times as heat continues to diffuse inward. This scenario would match the earlier anomalies in jet orientation and brightness changes. It is consistent with what we would expect from an object exposed to complex interstellar conditions: uneven radiation history, mixed materials, and thermally fractured subsurfaces. A more complex scenario is that the comet's outbound acceleration could reveal signs of structural asymmetry. Even though HiRISE found no large-scale fragmentation, the nucleus could still be elongated or unevenly dense. If so, the comet may experience small but noticeable shifts in how sunlight heats different sections of its surface as it rotates. This would create subtle periodic adjustments to its path. Detecting such a pattern requires highly precise measurements and may only be possible if the comet remains bright enough over the next several months. Another important factor is the way the coma begins to thin. As dust output decreases, sunlight reflects off a smaller halo, allowing more accurate tracking of the nucleus's exact position. This clarity makes it easier to detect faint deviations caused by jet forces. If scientists observe that acceleration changes correlate with shifts in the coma's brightness distribution, it may help identify which surface regions are still active, even without direct imaging resolution. Meanwhile, astronomers are paying attention to whether 3I Atlas develops a tail transition event, a shift in the direction or structure of the dust tail as activity declines. These transitions can reveal changes in dust, size, ejection speed, and solar wind interaction. In some comets, tail transitions mark the moment when deep, volatile-rich layers begin to freeze again. For 3I Atlas, a distinctive tail transition could confirm whether the earlier asymmetry seen in HiRISE images was tied to a specific active region or was part of a more complex, rotating pattern. The outbound trajectory also gives an opportunity to detect any late-stage structural stress. As the comet cools, differential contraction across the nucleus can create fractures. While these are far too small to resolve directly, they can cause abrupt but minor surges in activity, short-lived thermal events that slightly alter the comet's path. If such outbursts occur, they would provide additional clues about internal layering or density variations. All of these subtle behaviors will be measured against the backdrop of the comet's hyperbolic escape path. Because 3I Atlas is interstellar, even slight acceleration differences can influence long-term trajectory calculations, helping scientists estimate the comet's angle of entry, original speed, and potential region of origin. The outbound leg is therefore not just about understanding what 3I Atlas is right now, it also helps reconstruct where it came from. The broader question emerging from these outbound observations is straightforward. Will the final movement of 3I Atlas look like a typical comet leaving the inner solar system, or will it retain the same irregularities that have defined its inbound journey? Determining where 3I Atlas originated is one of the most scientifically interesting challenges associated with this object. Unlike solar system comets, whose orbits loop back around and offer repeated observation windows, interstellar objects appear only once. After a brief period of visibility, they leave forever. That means astronomers must use every inbound and outbound measurement to reconstruct the object's past, mapping its path backward across tens of thousands of years to identify the region, or at least the type of environment, from which it was ejected. The process begins with determining the comet's incoming velocity vector with precision. 3I Atlas has a clearly hyperbolic trajectory, which confirms it arrived from beyond the gravitational influence of the Sunday. But the exact direction of its incoming path carries uncertainties that are heavily influenced by small forces like jet-induced acceleration. As new outbound data refines those forces, astronomers can recalculate the original inbound direction. Even minor changes, fractions of a degree, can shift the predicted origin by several light years. Current preliminary models suggest that 3I Atlas did not arrive from a well-defined stellar system like Alpha Centauri or Vega. Instead, its probable origin lies somewhere within the local galactic environment, a region of moving star groups and drifting gas clouds. Many interstellar objects likely form in small, dynamic star-forming regions, then get scattered into interstellar space through gravitational interactions with young stars or giant planets. If 3I Atlas followed this common pathway, it may have been wandering for millions of years before entering our solar system. This idea is consistent with what astronomers know about 1I Oumuamua, and 2I Borisov. One of the specific clues researchers look for is the velocity dispersion, how fast the object was traveling relative to nearby stars before it entered the inner solar system. 3I Atlas's entry speed, corrected for solar gravity, appears to fall within the range expected for objects ejected from young planetary systems. This is an important detail because it suggests the comet was not accelerated by any exotic event. Its motion is typical of natural interstellar debris. Another piece of the origin puzzle comes from chemistry. The early Webb spectroscopy showed a strong carbon dioxide signature. While this does not pinpoint an exact star system, it does provide insight into the temperature and composition of the disk where the comet formed. High CO2 abundance is common in moderately warm regions of protoplanetary disks, typically near the boundary, where water ice transitions to vapor. If 3I Atlas formed in such an environment, it may have originated from a zone closer to its star than most comets in our own system do, possibly indicating a denser or more volatile rich region. Researchers are also analyzing the dust composition within the coma. Certain dust-to-ice ratios can suggest whether an object formed in a dense cluster environment or a more isolated region. A higher dust fraction, for instance, can indicate formation near massive stars whose radiation alters disk chemistry. Initial data for 3I Atlas does not show anything unusually high or low, but more detailed analysis is still pending. If the final measurements show anything distinctive, it could point toward a specific type of stellar nursery. Another line of inquiry involves galactic dynamics. Because stars drift and orbit the galaxy at different speeds, tracking an interstellar object's origin requires projecting its trajectory backward thousands of years while accounting for stellar motion. This process is complex and sensitive to small uncertainties. If 3I Atlas continues to show irregular acceleration on its outbound path, those uncertainties will grow, limiting how precisely researchers can identify its source. If its acceleration stabilizes, the range narrows, allowing for a more confident origin estimate. While scientists do not expect to pinpoint a specific star, the goal is to identify a region of origin, a cluster, association, or moving group with chemistry that matches the object's observed properties. If future data supports a volatile rich formation environment, 3I Atlas may trace back to a young, active star-forming region. If the chemistry appears more uniform and water-dominated, its origin may lie in a colder, more distant disk. Everything depends on whether the final trajectory data becomes more precise as activity declines. This raises the next key topic: how researchers will combine compositional data, trajectory modeling, and activity measurements to construct the most complete picture of 3I Atlas before it disappears from view. Bringing together the chemical, photometric, and trajectory data is one of the most complex parts of studying an interstellar object. No single measurement is enough to characterize 3I Atlas. Instead, astronomers must align multiple incomplete datasets and look for consistent patterns. This integration process is meticulous, and for an object that is only visible for a short time, every observation becomes part of a larger framework. The foundation of this framework is the comet's orbital solution. This defines its exact path through the inner solar system and serves as the baseline for every backward propagation model of its origin. To refine this orbital solution, astronomers combine high-precision astrometry from ground-based telescopes with the enhanced positional accuracy obtained from space-based platforms. Even though HiRISE did not directly alter the trajectory data, its constraints on the nucleus's size, activity level, and asymmetry help refine estimates of non-gravitational forces. These refinements then factor into the trajectory modeling. At the same time, scientists integrate spectroscopic datasets. Each instrument covers different parts of the electromagnetic spectrum. Webb observes mid-infrared signatures that reveal volatile ices and dust composition. Hubble captures ultraviolet and visible light reflections that map how energy is being absorbed and re-emitted. Ground-based telescopes fill the gaps with wide-field optical and near-infrared measurements. By aligning these data sources, researchers can track how the comet's chemistry changes over time and how those changes correlate with its activity patterns. A third component is coma morphology, the evolving shape of the halo surrounding the nucleus. This includes not only jets and brightness distribution, but also subtle rotational signatures that may be embedded in the diffuse material. Although the nucleus remains too small for direct resolution, rotational clues can appear as periodicities in dust flow, asymmetric arcs, or changes in the alignment of faint tails. Scientists combine morphological patterns with spectroscopic and activity data to infer which regions of the nucleus are most active and how surface features evolve over time. The next layer is the study of non-gravitational forces. These forces, driven by jets and sublimation, create small but measurable effects on the comet's trajectory. By comparing measured positions with predicted ones, astronomers compute how strongly these forces act at different times. Integrating this information with the chemistry and morphology data can reveal which volatiles are driving the acceleration, how the jets shift over time, and whether the activity is concentrated in a few vents or distributed across the surface. What makes 3I Atlas particularly challenging is that these datasets do not perfectly overlap in time. Webb captured some of its early brightening, Hubble followed later, coma development, HiRISE imaged the nucleus during a specific viewing window. Ground-based arrays provide continuous but lower resolution coverage. To produce a coherent model, scientists must interpolate between observations and identify consistent behaviors that persist across multiple datasets. Once the data are integrated, astronomers construct multi-parameter models. These models simulate hypothetical nucleus shapes, thermal conductivities, volatile distributions, and rotation states. Each simulation is then checked against the real-world measurements. If a simulated object shows similar jets, spectral changes, and acceleration trends, it becomes a strong candidate for representing 3I Atlas's true structure. If it conflicts with observations, it is ruled out. This cross-verification process eliminates many possible explanations, but often reveals new ones. For example, a simulation might show that a slightly elongated nucleus with a deep CO2 reservoir could reproduce the irregular jets and mass loss observed early on, but only if the rotation state matches specific parameters. These interactions between variables help researchers narrow down realistic scenarios. As new data continues to arrive, the integrated model becomes more refined. However, certain uncertainties will remain due to the inherent limitations of remote observation. No telescope can image the nucleus directly at fine resolution. No spectrograph can probe deep below the surface. Every conclusion involves degrees of statistical confidence rather than absolute certainty. The strength of this integrated approach is not that it reveals perfect answers, but that it identifies which physical interpretations are most consistent with the combined evidence. It creates the closest possible approximation of what 3I Atlas is, where it came from, and how it behaves. Which leads to the next critical layer of the story: how 3I Atlas compares to the only two interstellar objects humanity has ever observed, Oumuamua and Borisov, and what that comparison tells us about diversity in interstellar debris. With the broader model of 3I Atlas taking shape, the next step is comparing this object to the only two interstellar visitors ever observed before it: 1I Oumuamua and 2I Borisov. Each of these objects displayed behaviors that stretched or challenged existing comet and asteroid models. Together, they form the beginning of a statistical sample small, but enough to hint at emerging patterns in interstellar debris. Understanding where 3I Atlas fits among these rare visitors is essential for determining whether its anomalies are unusual or simply part of a wider diversity we're only beginning to recognize. The first interstellar object, Oumuamua, was detected in 2017. It exhibited no detectable coma or tail, showed an unusual light curve consistent with an elongated or possibly flat shape, and displayed small, non-gravitational accelerations without evidence of outgassing. These accelerations remain debated. Some researchers proposed exotic ices or extremely low-density material. Others suggested geometric effects or sublimation not visible to telescopes. While Oumuamua sparked speculation, no theory fully explains its behavior. Importantly, its lack of detectable gas or dust made composition analysis extremely limited. The second visitor, 2I, Borisov, discovered in 2019, looked more familiar. It behaved like a classic comet, clear outgassing, a typical dust tail, and spectroscopic signatures that matched known cometary materials. However, Borisov also showed signs of fragmentation, unusually high dust production, and chemistry that differed from most solar system comets, particularly in its high levels of carbon monoxide. These features suggested it formed in a colder or more volatile rich region than typical comet nurseries around sun-like stars. Now 3I, Atlas, adds a new data point, and it sits between these two extremes. It is not bare and silent like Oumuamua, but it is not as straightforwardly comet-like as Borisov. Instead, it shows moderate but unusual activity, significant CO2 release, uneven jets, and a stable nucleus that has not fragmented significantly. This intermediate behavior hints at a different formation history and environmental origin. One important comparison lies in volatile composition. Borisov contained high CO and water ice content. Oumuamua's composition remains almost entirely unknown. 3I, Atlas, by contrast, shows strong carbon dioxide signatures with uncertain amounts of water and carbon monoxide. This may indicate a warmer or chemically distinct region of formation. The diversity across the three objects suggests that interstellar comets may span a wide range of chemistries, reflecting the many types of protoplanetary disks across the galaxy. Another comparison comes from activity patterns. Borisov's activity was intense and consistent, driven by standard cometary physics. Oumuamua had no visible activity, but still accelerated slightly. 3I, Atlas displays visible outgassing, but its jets are uneven and somewhat unpredictable. This places it closer to Borisov, but with notable differences. Researchers now believe that irregular activity may not be unusual for interstellar bodies, especially if their surfaces or internal structures were altered by cosmic radiation or prolonged exposure to deep space thermal cycling. Shape and nucleus structure also distinguish these objects. Oumuamua was highly elongated or possibly pancake-shaped based on light curve analysis. Borisov was more conventional, with a nucleus likely a few kilometers across. HiRISE shows that 3I, Atlas, is compact, rugged, and asymmetric, but not extreme in shape. This further supports the idea that interstellar debris exhibits wide structural variation. Finally, there is the question of non-gravitational acceleration. Oumuamua's acceleration sparked years of debate. Borisov's was typical and explained by sublimation. 3I, Atlas falls somewhere in the middle. Its acceleration is real but irregular, consistent with uneven outgassing. This reinforces that non-gravitational forces are likely to be a key diagnostic tool for future interstellar objects, helping distinguish whether their activity is driven by typical cometary processes or more complex internal dynamics. As the catalogue of interstellar objects grows, astronomers expect to see even more diversity. If 3I, Atlas, is any indication, these visitors may span a continuum from inert rocky bodies to highly active comets, each shaped by the unique environment of its origin. This comparison raises a broader scientific question. How do objects like 3I, Atlas, survive millions of years of interstellar travel without disintegrating? And what does their survival tell us about their physical resilience? One of the most surprising aspects of interstellar visitors is that they survive the immense stresses of deep space at all. Over millions or even billions of years, objects like 3I Atlas travel through environments far harsher than anything found inside the solar system. They experience extreme temperature shifts, high-energy cosmic radiation, and occasional gravitational encounters with stars or giant planets. Understanding how such objects remain intact provides another angle for interpreting the unusual behavior observed in 3I Atlas. A major factor in interstellar durability is cosmic ray processing. For objects drifting between stars, cosmic rays continuously bombard their surfaces, breaking molecular bonds and reorganizing chemical structures. Over long periods, this forms a hardened radiation crust, a few centimeters thick. This crust can trap volatile ices beneath it, shielding them from escape. When an object finally enters a new planetary system and begins heating, the defy, trapped gases, may vent through narrow cracks, creating uneven jets. This mechanism fits well with the activity patterns seen in 3I, Atlas, and may explain why its outgassing does not follow simple rotational or thermal models. Another survival mechanism is thermal cycling resilience. As an interstellar comet drifts through space, its temperature may swing by hundreds of degrees depending on its distance from nearby stars. These intense cycles can cause the outer layers to fracture, producing a shell of dust-rich material that gradually stabilizes. Paradoxically, this fracturing process can reinforce the nucleus, loose material between cracks, cushions, stress, and prevents the object from breaking apart completely. If 3I, Atlas, underwent such cycles, it would exhibit internal voids and heterogeneous layers, precisely the types of structures that could cause irregular jets and inconsistent brightness signatures. Gravitational encounters also play a role in shaping interstellar survivors. When a small body passes near a star or massive planet, tidal forces can strip away loosely bound material. Over many encounters, only the most cohesive, solid core fragments remain. If 3I, Atlas, originated in a dense star-forming region, it may have experienced multiple flybys during its ejection from its home system. This process would naturally remove weak outer layers while leaving behind a compact, resilient nucleus. HiRISE's observation of a single intact core fits this pattern well. A fourth factor is collisional history. Interstellar space is sparse, but not empty. Tiny dust grains, micrometeorites, and ionized particles collide with passing objects at high speeds. Over time, these impacts can create pits and microcracks, while also compacting parts of the surface. Such impacts produce a textured, uneven exterior that affects how heat is absorbed and released. This could explain why different regions of 3I, Atlas, appear to activate unpredictably localized. Heating may reach buried volatile pockets at different times. All these mechanisms result in an object that is both hardened and fragile. The surface may be rigid and protective, while the interior is fractured and irregular. This duality is consistent with everything astronomers have seen in 3I, Atlas, an intact nucleus with uneven outgassing, irregular heating, and a coma shaped by deeply embedded processes. Another piece of the resilience puzzle involves material composition. Some volatiles commonly found in interstellar objects, particularly CO and CO2, are more resistant to sublimation in cold environments, but vaporize rapidly under solar heating. This dual behavior can produce dramatic but controlled activity. 3I, Atlas's strong CO2 signature suggests it may carry large amounts of such material, allowing it to remain dormant for long periods before suddenly becoming active near a star. One of the more intriguing research questions is whether the surfaces of interstellar comets contain exotic ice phases, molecular structures formed under extreme pressures and temperatures not typically seen in solar system comets. These phases could affect how heat moves through the nucleus, how jets form, and how quickly the coma expands. While no direct evidence of exotic ices exists yet for 3I, Atlas, the idea remains on the table because it could account for some of the irregularities seen in early spectral measurements. At present, it remains unconfirmed and should be considered speculative. As astronomers study 3I, Atlas, in more detail, they are also trying to understand how long objects like this can survive before breaking apart. Evidence from other interstellar candidates suggests that fragments formed in one system can travel intact across large regions of the galaxy. 3I, Atlas, is likely another example of this surprising durability. This leads to a deeper question. How common are interstellar comets like 3I, Atlas, and what does its survival tell us about the number of similar objects that might pass through our solar system in the future. As 3I Atlas continues its outward path, the opportunity to study it is slowly closing. By early 2026, the comet will fade beyond the reach of most telescopes, and the final datasets will be all that remain. Yet even with incomplete information, scientists have already learned more from this single visitor than they expected. The object has confirmed that interstellar comets are not uniform. They carry different chemistries, different structures, and different activity patterns shaped by environments that vary widely from star system to star system. The HiRISE images gave us our first close look at the nucleus of an interstellar body, showing active outgassing. They showed a small, rugged, intact core. They revealed uneven jets, asymmetric brightness, and a halo shaped by complex internal dynamics. They ruled out major fragmentation, exotic structures, or any behavior that would require physics beyond what we already understand. At the same time, they confirmed that the activity does not follow the simple patterns seen in many solar system comets, a reminder that nature often operates on a spectrum much wider than our initial models assume. Combined with the data from Webb, Hubble, and ground-based observatories, 3I Atlas now stands as a bridge between the two previous interstellar visitors. It is more active than Oumuamua, more irregular than Borisov, and more chemically distinct than either. Each dataset adds another layer of detail, and together they point toward a single, coherent interpretation. 3I Atlas is a natural object, shaped by a formation environment very different from our own, now revealing its internal structure as sunlight activates layers left untouched for millions of years. There are still unanswered questions. How deeply layered are the volatiles? How irregular is the rotation? How much internal fracturing exists? Where in the galaxy did this object form? These are questions that may never be answered with full precision, but they are questions that will guide the next decade of interstellar research. And when the next object arrives, whether in 5 years or 50, the lessons learned from 3I Atlas will help scientists recognize what is typical, what is unusual, and what new features may point toward previously unseen physics or chemistry. For now, 3I Atlas remains what it has been since the day it was discovered. A rare, natural visitor from another star, carrying the history of a distant world in its frozen structure. The data we gather today will be the only record humanity ever has of it. If you want to follow every new observation as it's released, subscribe and turn on notifications. And tell me in the comments which part of 3I Atlas do you think will remain the biggest mystery long after it leaves our solar system?